Hi! In this video, we will answer some of the questions that we have received on our Introduction to PID presentation. Let's get started. Question 1. What does the result of the PID controller look like?
As you recall, in our Introduction to PID Control video, we mentioned several types of controllers, including P, PI, and PD. In the context of the robot arm example that we introduced in the video, the P, proportional part, gets the arm moving towards the target position, and the I, integral part, helps get rid of the offset. But what does the D, derivative part, do? It provides a damping effect, which means it reduces fluctuations of the system's behavior. Here's an example to illustrate this. Suppose that this is the response of a system to a P proportional controller. If we add an I integral part, forming a PI controller, the system response may look something like this. Now let's look at the effect of a PD controller. Notice how the PD curve has a reduced oscillation. The D part has dampened the curve. Question 2. Would the PI controller handle all disturbances?
The answer, simply put, is no. When a system is subjected to load disturbances, like when the weight that a robot is carrying increases suddenly, the integral of the error function could increase significantly. This in turn could result in windup, which amplifies the system's oscillation and increases the settling time. Therefore, it is important to exercise care in selecting a controller and to properly tune it in order to achieve the expected outcome. Question 3. It looks like the PID controller gives the best performance. Should we always use PID instead of P, PI, or PD?
There is no one best controller type for all situations. Generally, the type of system that we're trying to control and its expected behavior dictates the type of controller that we want to use. For example, if a system mandates minimal oscillation, but offset isn't a huge concern, we may want to use a PD controller. On the other hand, if we're looking for a small offset, a PI or PID controller may be a better choice. Question 4. What are the different systemic methods for determining the gains?
In the previous video, we talked about three coefficients: the proportional, integral, and derivative gains. In the robot arm example that we used, we showed how the controller determined the speed of the motor using these coefficients, as shown here. Speed equals P gain times error, plus I gain times integral, plus D gain times derivative. There are three different methods for calculating the gains: trial and error, classic tuning, such as the Ziegler-Nichols method or the Cohen-Kuhn method, and software simulation. We will discuss some of these in more depth in a later video. Question 5. How does one deal with noise?
If you remember from our Introduction to PID Control video, noise is quick random changes in the input signal, which results in rapid fluctuations of the error, and it can be caused by various things, like vibration or electrical interference. Now let's say we have a noisy signal, so you want to get rid of the noise, to filter it out. How do you do that? Let's use a metaphor here of a smoothie. So you go out one day and buy a smoothie, but once you start drinking it, you realize that it tastes kind of strange. You can't figure out exactly where the strangeness is coming from, but you're really curious, so you decide to go home and recreate the smoothie. Because when you figure out all of the ingredients, you can taste them individually and find out which one or ones are making the smoothie taste strange. Now let's put that in more technical terms. The smoothie in this example is actually your signal. How do you break down a signal? Well, a mathematician named Joseph Fourier proved that most functions can be decomposed into a number of sinusoidal functions, such that if you add up all of these sinusoidal functions, you'll get the original function. Just like if you add up all of the ingredients, you'll get a smoothie. When we replace a function with a set of sinusoidal functions, it becomes much easier to get rid of the noise. But how? Suppose we have a noisy signal like this. This could be the error function for a system that is being controlled. According to Fourier, we can decompose the function into a series of sinusoidal functions like this. It is important to note that noise is generally characterized by a high-frequency signal. Assuming our original error function is noisy, the signal shown in red, the one with the highest frequency, must be noise. If we get rid of it, the two remaining signals look like this. If we add the remaining signals together, we get this. This represents our error function, but without noise.
Hopefully this has helped answer some of the questions you may have had. But if not, or if you have any further questions, feel free to comment below or email us at g@vex5757.net. Thank you.